Hi and welcome to this tutorial on oxidation numbers. So in the previous tutorial we learned about the equilibrium constant Kc. Now we're going to move on to a different topic. So we're going to look at oxidation and reduction, a reminder of what that means, and we're also going to look at oxidation states and how to work out the oxidation states of compounds and particles and molecules, ions, everything basically. So key terms you obviously need to know: oxidation and reduction. We're going to talk about redox reactions and what the process of oxidizing and reducing actually involves. A reminder, if we're talking about oxidation, we are talking about the process of electron loss. And oxidizing agents are electron acceptors, meaning the other compound gets oxidized and they themselves get reduced. They're an oxidizing agent, so the other compound that they're acting on gets oxidized. And then when we're talking about reduction, we're talking about the process of electron gain. And reducing agents are electron donors. So they themselves get oxidized and the compound that picks up, or the atom that picks up those electrons, is reduced, hence it is a reducing agent. So of course we're going to remember our abbreviation or acronym OIL-RIG, which you would have learnt at GCSE and is just as useful now. So oxidation is loss of electrons and reduction is gain of electrons. When we have a redox reaction, all we're saying is that reduction and oxidation have happened at the same time in that reaction. So as I mentioned before, we've got things called oxidizing agents and reducing agents. So oxidizing agents themselves get reduced by accepting electrons, gain, RIG, and reducing agents themselves get oxidized by donating electrons. And if we're working out the oxidation state, or number, that's what we mean, oxidation number, it's the total number of electrons that that element has either gained or lost. So that they've either gained by accepting for another element or removed from another element. And if they've gained, if they've accepted electrons, then they're going to get a negative oxidation number. And if they've removed electrons, they're going to get a positive oxidation state or oxidation number. It makes sense. Electrons are negative, so if you lose the negativity, you're going to start feeling more positive. So we've got oxidation is an increase in oxidation state or number, and reduction, we can tell when something's been reduced because we get a decrease in the oxidation state or the number. Let's have more of a look of what we mean by oxidation state or oxidation number. So we've got a number values attached to this. So if we look at the example of potassium chloride, we've got potassium and chlorine reacting. Obviously, these are just their atoms, and we're making potassium chloride. So we can see that potassium has lost an electron. It has fully transferred that electron over to the chlorine. So potassium, losing that negative electron, has now got an oxidation state of +1. And our chlorine, or our Cl, because obviously I think of chlorine as a diatomic chlorine, but our chlorine atom has overall gained an electron, so it's going to have gained one negative charge. So its oxidation state is going to decrease to -1, from 0 to -1, and therefore that's reduction. So we know that potassium's been oxidized because it's gone from 0 to +1. And the chlorine atom has been reduced because it's gone from 0 to -1. When we do our oxidation states, we always want to make sure that that symbol, the plus, is before the number. When we talk about ions, so if we have a potassium ion, let's not pick potassium, let's pick one with a number. So calcium, we do our ion with the number first and then the plus afterwards. Whereas when we do an oxidation state, the oxidation state of calcium is the oxidation state of a calcium 2+ ion is +2. Note how I put the plus in front. You will lose a mark if you put the plus afterwards if you write 2 plus. The way I remember that is quite a silly way. Oxidation states, we're talking about oxidation numbers. There's an X there, and the X is like a plus on its side or slightly reorientated. So that always reminds me that when I'm talking about oxidation numbers, I have to put the plus or the minus in front of the number. And when it's an ion charge, I just put the number first. That's actually really helpful. I see lots of students making that error in their exams. Let's look at another example then. So ions form a number of different, or ion forms a number of different ions. So I mentioned this in a previous tutorial. When you're writing your answers, you need to say ions. So here we've got ion forming a 2 plus ion. And you can see that that is because it has lost 2 electrons. There they are there. And you can see this equation is balanced. The charges are balanced. So I've got 2 minus charges, 2 plus charges, and on this side, nothing. So we formed the 2 plus ion. We can form it by oxidizing the metal. Yeah, so by removing those electrons, oxidation is lost. We need to oxidize this ion here. And we now say that the ion has got an oxidation state of +2. So like I said, you can see that its ion charge is 2 plus, but its oxidation state, we put the plus first, is +2. And if we remove another electron, so here we've got our ion, losing one more electron, we're now going to have an oxidation state of +3. There are some rules for assigning oxidation states. Practice makes perfect, so you need to learn these and then you need to practice a lot, especially considering the exceptions. So there are a few things that you can always guarantee. Group 1 and Group 2 metals are always +1 and +2 respectively, and fluorine is always -1. So that really helps. Knowing those, there are no exceptions. For oxygen and hydrogen, they're usually the ion that they would form. But we have got a few exceptions, so metal hydrides and peroxides. Peroxides meaning something like H2O2, that's a peroxide. And they do like to use the exceptions quite a lot in exams because they exist, so they do try and catch you out sometimes. And chlorine, group 7s in general can have variable oxidation states, except for fluorine, of course. So chlorine, iodine, bromine, etc., they can have -1, +1, +3, +5, or +7. So there's quite a few different oxidation states they can have. You'll find that chlorine is usually -1, except in compounds with oxygen or fluorine. But yeah, group 7 can be quite interesting, but there still are only a limited number of different states that they can have. The transition metals, so the D block elements, most of the D block elements, are known for having lots of different ion charges, and they've got loads of different oxidation states. That's partly why they're so colourful. The different oxidation states have different colours. And then we've got some rules that you need to follow. So you need to memorize those rules in the previous slide, and there's a few more here. So the oxidation state of an uncombined element is 0. So for example, if we were just looking at magnesium metal, if I just pick magnesium, that is 0. It is uncombined and it's by itself. The sum of the oxidation states of all the atoms or ions in a neutral compound is 0. So if I picked something like NaCl, we know that Na is going to be +1 because it's in group 1. Chlorine's going to be -1. But overall, the oxidation state, +1 plus -1, is 0. The sum of the oxidation states in all the atoms in a simple monatomic ion is the charge of the ion. So let's take magnesium and instead let's have it as its ion. So the oxidation state of magnesium 2+, imagine if it's in a solution, for example, is +2. It's just the charge on the ion. The overall oxidation state of a compound equals the overall ion charge. That's helpful for polyatomic ions. So if I pick something like SO4 2-, so a sulfate, which if it combines with hydrogen, it makes H2SO4, sulfuric acid. All of these together are going to add up to a total charge of -2. So I'm going to have 4 -2s from the oxygen, taking me down to -8. And sulfur is going to be +6. So +6, and each of those oxygens is going to be -2. And that is overall going to give me an overall charge of -2 because it needs to equal the charge on the ion. Elements existing as molecules with identical atoms bonded have an oxidation state of 0. So O2 and Cl2, for example, have an oxidation state of 0 because we've got identical atoms. There's no loss or overall gain. The more electronegative something is, the more negative its oxidation state or oxidation number is, and the less electronegative, the less negative the oxidation state is. Remember, in the periodic table, we tend to increase in electronegativity as we move into the top right-hand corner. So it's at that sort of angle. So that's a helpful rule. And then some elements almost always have the same oxidation states in their compounds. That's something that's helpful to know. So transition metals are known for having different charges and different oxidation states. There's quite a lot of types that don't. And then Roman numerals help tell us the oxidation state, and this is mostly helpful for the transition elements. But iron is a good example as well. So if you see iron 2 chloride written down, that means we've got Fe2+ and Cl- making a compound, and you would balance that accordingly in terms of making the compound. So it would be Fe2Cl. Okay, and we can have iron 3, which would mean it'd be an Fe3+. Let's have a go at working out the oxidation states then. So we've got work out the oxidation state of this complex transition metal ion. Now, you don't do transition metal ions till the A2 course normally, but we can still work this out. And there's a trick here. So we know that the overall oxidation state charge of everything added together is going to be equal to the charge on the compound, which is +3. Because there's my charge 3+. So the oxidation states of chromium plus 6 water molecules has to equal to +3. Now I know my water molecules are neutral, so I can take a shortcut. Okay, the metal atom is surrounded, or iron is surrounded by neutral water molecules. So I know that that's going to be 6 times 0. So there's going to be nothing from the water, and then we're not going to know our CR effectively, but the chromium must therefore be +3. That's the oxidation state on our chromium. What about the oxidation number of phosphorus in this compound here? So pause the video and give it a go yourself. Here I'm looking at the fact that the overall charge is nothing. There's no overall charge in this compound, so everything has to be equal to 0. And I like to do a little bit of sort of basic maths for this, bit of algebra. So this isn't an exception for hydrogen, so it's going to be +1. And we've got 5 hydrogen atoms. So 5 times 1. It's not a metal hydride, that's why it's not an exception. I've got phosphorus. Now that's what I don't know. So I'm going to have 3 times P. And I'm going to define, there's a temptation to use X, but OCR, for example, have recently stated they want you to define the terms rather than use X. So I'm telling the examiner that I know that I'm looking for phosphorus there. And then I've got oxygen. Now this isn't an exception for oxygen, it's not a peroxide. So we're going to have 10 times -2. And then I solve for P. Yeah, so I've got lots of information here. So if I solve for P, I'm going to end up with P equaling +5. So a little bit of algebra. Then finally, have a go at this one. So using what we've just learnt. So again, the overall charge is equal to 0 because there is no overall charge in this compound. And I know oxygen, because it's not an exception, it's not a peroxide. So we're going to have 2 times S, the unknown, plus 3 times -2. Each oxygen contributes -2. So if I solve for S, S equals +3. Note how we always, like I said before, put the plus sign before the number. If you put it after and write 3+, you will lose a mark. That is incorrect and will not be accepted. And again, we know that this is going to be equal to 0 because there's no overall charge on this compound. And we don't know phosphorus, but we know there's 2 of them, so 2 times P. And we know there's 5 oxygen molecules. It's not an exception for oxygen. It's not a peroxide. So I'm just going to give oxygen its oxidation state of -2 because it's in group 6. And so if I solve for P, I get +5. For our next, it's also going to be equal to 0. I have been asked to work out the oxidation state of chromium. That's the one I don't know. I've got 2 sodium atoms. Now, sodium's in group 1. Group 1 always has an oxidation state of +1. So I've got 2 +1s, plus 2 times Cr, because I don't know that, plus 7 times -2. It's not an exception for oxygen. It's not a peroxide. So if I solve for this, so solve for Cr, I get +6. And finally, having a look at this one, we want the oxidation state of sodium. Now, sodium's in group 1, so we know it's going to be +1. So I don't need to do anything here. Sodium is always +1 because it's in group 1. And that's one of our rules.